Hey everybody, Dr. O here, and welcome to USLO 2.2. In this video, we're going to be talking about the definition of an element, and then we're going to get into the definition of molecules and compounds. Now, I don't believe your syllabus asks you the definition of a molecule versus that of a compound, but I'm going to give you that anyway. And then within compounds, we're going to look at how compounds are created, whether it's ionically bonded or whether it's covalently bonded. So we'll be learning what the difference is with that. Now, within each one of those, we're going to be learning some language as well. So for under ionically bonded compounds, we're going to learn what a cation is and what an anion is. And we're going to learn the definition of an electrolyte. Under covalently bonded molecules, we're going to learn what is a nonpolar bond, what makes up a nonpolar covalent bond, versus what makes up a polar covalent bond. And then our last sort of bond that we're going to talk about really isn't a real bond at all. It's actually an attraction between molecules, but we still call it a bond, and that is the hydrogen bond. So let's get started. So on this slide, we have elements, molecules, and compounds. So let's look at a diagram to define each one of these, and then we'll actually give it some words. So let's start off by talking about elements. What are elements? Well, we've got a periodic chart of elements. We could go there and look, and I'll tell you some examples would be hydrogen, nitrogen, and oxygen. And then we have this category called molecules. So what is that? Well, an example of a molecule would be, what if we took a couple of hydrogens and put them together? This would be an example of a hydrogen molecule, hydrogen gas specifically. We could do the same thing with nitrogen, forming some nitrogen gas, and oxygen would come together to form a molecule of oxygen gas. Now, within molecules, there is a subcategory that we call compounds. So what falls within this? Well, let's use hydrogen as an example. Let's say that we took hydrogen and we added it to some oxygen. We would form a water molecule. Or we could take nitrogen and add it up with some oxygen and we could create nitric oxide. Or we could take our oxygen and put it with some sulfur and create sulfur dioxide. All of these are molecules because they are two or more atoms together. But these compounds involve two different atoms. So this is kind of a scenario where a square is a rectangle, but a rectangle isn't a square. So we have compounds are molecules, but molecules aren't necessarily compounds. That sort of scenario, because these are all molecules, but hydrogen gas is not necessarily a compound because it's two of the same atom. So that's what we're talking about when we're making the distinction between molecules and compounds. So let's actually put some words to this. What makes up elements? Atoms. And what are some examples? Hydrogen, nitrogen, oxygen, anything you pluck off the periodic chart. So molecules, how would we define molecules? Two or more atoms bonded together, and examples would include hydrogen gas, nitrogen gas, oxygen gas, as well as water, nitric oxide, sulfur dioxide. And compounds, being a subset of molecules, would be two or more different atoms bonded together. And our examples would be water, nitric oxide, sulfur dioxide, but not hydrogen gas, nitrogen gas, or oxygen gas, because those are just molecules. Now, when we're forming compounds, the type of bond that's going to hold them together makes a difference. And here on the slide, we're starting off with ionically bonded compounds. So we have to first of all ask, what is an ion? Well, an ion is an atom that has either gained or lost electrons. And the reason why it does that is because it improves the stability of the atom in doing that. So as a result of either gaining or losing electrons, that means that now we're going to have an imbalance in the number of electrons compared to the number of protons, and that means that this atom is now going to bear some sort of a charge. So for example, you might have seen calcium written with that 2 plus up in the superscript on the right. You might have seen hydrogen written the same way, or oxygen written with a 2 negative, chloride written with just a negative sign out there. All of these are telling you about the electrons that were either lost or gained. And we're going to look at how these get calculated in just a second. Now, we notice that we have a couple of terms with positives in the superscript and a couple with negatives, and we have names for these. A cation is an ion that's going to bear a positive charge, and these are going to be atoms that have lost electrons. Now, if we think about this, if we start off with the same number of protons and electrons, same number of positive charges and same number of negative charges, and we lose some of those negative charges, then what we get left is a surplus of positive charges. We're going to do a calculation, and we'll get to that. Now, the opposite of a cation is going to be an anion, and these are going to be ions that bear a negative charge as a result of having gained electrons. So if we think about this, typically we're thinking about atoms that have the same number of protons, same number of electrons, but if we pick up an extra electron or 2 or 3, then we have to let the reader know that that happened, and we do that by putting a negative in the superscript on the right. So that's how that works. So let's take a look at this, do a little bit deeper dive. So I said that ions are created because it creates stability, and it all has to do with the octet rule. Yeah. So let's take a look at sodium and chloride. So sodium, and I'm not going to go through the trouble of filling in what's happening in the nucleus. You'll just have to trust me. But we can count the number of electrons. So we have 2 here in this inner orbital, and then we have an octet here in the second orbital. So 2 plus 8 gives us 10, and then here's 11. So we've got 11 electrons, and we're going to assume that we've got 11 protons as well, because I'm telling you we're dealing with sodium. Now over here with chlorine, we've got 17 protons in our nucleus. So we have, let's count our electrons. We have 2 here plus another 8, that gives us 10. And we have 11, 12, 13, 14, 15, 16, 17 electrons right here. Okay, now if we notice something about these two elements, both of them have 3 orbitals, but I only have 1 electron here in this orbital. Over here I have almost 8, missing 1. So in order to make this one, sodium, a little more stable, it would be really easy just to let this electron go. Just let it go. Because what would it leave behind? It would leave behind this octet right here, satisfying the octet rule. Now, if I let this electron go, maybe our chlorine would find it. And then if it found it, instead of having 7 electrons, it would now have 8. So let's go ahead and make that move. Let's just drop it in right there. Okay, so now that we've done that, what have we done to sodium? Well, now we've got 1, 2, 3, 4, 5, 6, 7, 8 electrons in our valence shell. So now we've created stability in our outer orbital. We're satisfying dun, 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 the octet rule. That's right. But because we've changed the number of subatomic particles, we have to let our reader know that. So let's count what we did here. So we know we're still dealing with sodium, which means that we know that we have 7 protons. We have 11 protons, which means that we have 11 positively charged particles, which gives us kind of an 11 positive charge. Now at present we only have 10 electrons, which means that we have a negative charge of 10. Now if we calculate the difference between a positive 11 and a negative 10, we're going to have 1 more positive than we have negatives. And the way that we're going to express that is to take the symbol for sodium and give it this positive right up here in the superscript and create a cation. Now let's work this same sort of calculation with chlorine. Now why does chlorine want to have this extra electron right here? Because it satisfies the octet rule for it. So let's do our calculation. So we're dealing with chlorine, which means that we're going to have 17 protons, which means we're going to have a 17 plus charge, a 17 positive charge. Now we had 17 electrons, but we gained one. So instead of having 17 negative electrons, we're now going to have 18 negatively charged electrons, which is going to give us a charge of negative 18. Now if we add a positive 17 and a negative 18, we're going to have one more negative charge than we have positive charge. And the way that we're going to let our reader know that that's what we have is we're going to take the symbol for chlorine, which is Cl, and we're going to put that negative in the superscript on the right, thereby creating an anion. So if you ever wondered what those little positives and negatives meant in the superscript on the right, that's telling you about the number of electrons that were either gained or lost. So as we just saw, when it comes to creating ions, it's going to, or even forming ionic bonds, is really all about the octet rule. So atoms desire to have 8 electrons in their valence shell. Except for the smaller ones like hydrogen and helium, they've only got room for 2 because they have only that first orbital, which can only hold 2. They're going to be driven to form a duet, which is called the duet rule. But for everything else, it's going to be the octet rule. So the desire to have 8 electrons is going to be the driving force behind chemical reactions, all chemical reactions. Now there is a group of atoms that already have 8 electrons in their outer orbitals, and these guys are called the noble gases. And as a result of having that complete valence of 8, they're basically not chemically reactive at all. You actually have to force them to undergo certain reactions. You have to kind of tweak the environment and make things happen with them. But otherwise, all the other elements, they're going to be driven to interact with each other based upon the octet rule. So, and the reason why is that most atoms don't have full valence shells, and it is the drive to have these full atom valence shells that are going to drive either the gain or the loss or even the sharing of electrons to create those unions that we call molecules or compounds. Because by doing so, either by losing or gaining electrons, it's going to drive that stability to have 8 electrons in the valence shell. So let's take a look at some of that. Now it's going to be ions that are going to form ionic bonds. So we can then say that ionic bonds are going to involve the transfer of valence electrons from one atom to another, and that's going to create the ions that we see. And in doing that, because one atom's going to lose the electron and form a cation, the other one is going to find the electron and form the anion. So in a transfer of valence electrons, we're going to have the creation of the anion, the negatively charged ion, and the positively charged ion, the cation. Now, when these two ions find each other, when a positive ion finds a negative ion, when a cation finds an anion, they're going to be attracted based upon those charges. And when we have this sort of union coming together, we call it an ionic bond. And these sorts of compounds, because they're going to be two different atoms, these compounds are going to be generically what we call salts. You heard me right, salt. So think about what you're putting on your food. That is technically a salt. It is comprised of a positively charged sodium coming together with a negatively charged chlorine. We call it sodium chloride. That's an example of a salt. Now, anything where you have a positively charged element coming together with a negatively charged, I should say ion, is going to be generically called a salt. And one of the qualities of salts is that when you put them in water, they separate into their ions. And we will say then that they form electrolytes in water. All that means is that the bond that exists between them when they're not in water gets disrupted and they go into their ionic state. So what does that look like? Well, let's have a peek. So let's say that we have a beaker of water right here and we have some salt, sodium chloride. Sodium chloride is an ionically bonded substance and generically what we call salt or a salt. And we're going to drop it into water. So let's drop it into water. It's going to separate and form sodium ions and these negatively charged chlorides. It's a chlorine ion. So then we could say that our salt is going to dissociate and form ions in water. And that is the definition of an electrolyte. So we could basically say that salt is an electrolyte. Now, if you ever wondered that, go grab a bottle of Gatorade, because Gatorade says, oh, it's filled with electrolytes. And if you read what's on there, you're going to find sodium chloride. Basically, it's salt. A much more tasty way to get salt, as far as I'm concerned, is to eat a potato chip. So I live in Texas, and when I'm out mowing the lawn, I keep a couple of things in I have a couple of lawns that I actually mow, and I keep potato chips in my car along with water because I replace my electrolytes by eating potato chips. Potatoes are full of potassium, another electrolyte, and salt as well, sodium chloride, and I get to restore some of my electrolytes that way. So, yeah. There you go. So there's a perfect example of why you need to study chemistry, so you can know what you're dealing with. So there's more than one ways to get electrolytes. You don't have to go to Gatorade. You can get the potato chips, eat a banana, learn where your electrolytes are, and focus in on those. Now, ionic bonds are not the only way that we get compounds. We can also form compounds or molecules through covalently bonding atoms together. So what do we mean by covalent? Well, it has to do with valence electrons, and it is specifically the sharing of valence electrons. So in this scenario, we have our atoms keeping the electrons that they show up with, which is different than what we saw with ionic bonds where we have the transfer of electrons. Somebody's given it up and somebody's finding it. In this one, everybody gets to keep the electrons that they show up with, but instead of transferring, they're going to share them, which is where the word covalent gets its meaning. So it's the sharing of the valence in order to form a bond. So let's look at an example of this. So let's bring up hydrogen. Now, what do we know about hydrogen? Well, we know that hydrogen has one valence electron in that first orbital. That first orbital can only hold 2 electrons, so we know then that hydrogen wants to have 2 valence electrons. That's all it can actually handle is the addition of one more electron to its one orbital. Now, oxygen is a little bit different. Oxygen is a bigger molecule. It has 6 valence electrons, but it has the capacity to have 8 in that outer orbital, so it actually wants to have 8 valence electrons. So let's see how this works between hydrogen and oxygen. So let's start off by looking at our oxygen right here, and to it we're going to add hydrogen. So hydrogen is going to show up with this one little electron, and it's going to share it with oxygen. But we still have a space right here that oxygen would like to have filled, so let's drop in another hydrogen like that. Now, what have we created? Well, we've actually created water, H2O. Now, in doing this, by adding this hydrogen to either side, each one with its electrons, what have we basically accomplished? Well, if we look at the electrons around oxygen, how many do we have? We have 8. We have thereby followed the octet rule. We have given oxygen 8 electrons in its valence orbital. Now it's happy. Now it's stable. Hallelujah. But what did we do for hydrogen? Well, if we look at what we got going on with hydrogen, hydrogen brought 1 electron to the party, and it gets to share 1 electron that oxygen has. And we've basically satisfied what hydrogen can handle, which is called the duet rule. We've completed the valence electrons that hydrogen is seeking to gain. So in this way, we have created stability for each of the two hydrogens as well as the oxygen by everybody sharing their valence electrons and creating covalent bonds. Now, I know I painted a very rosy picture on the previous slide about how if you have molecules formed through the sharing of electrons, everybody's got a full octet or a duet, and now everybody's happy and life is grand, right? Well, when it comes to covalent bonding and the sharing of electrons, there's a little bit more to it than that. And sometimes that sharing is not always as fair and equal as we might like to think. This is why we have polar and nonpolar bonds. So what does that mean? Well, it means that atoms have different electron attracting abilities. And based upon this, we can have either the equal sharing of electrons or unequal sharing of electrons. So, what's the concept behind that? Well, it has a little bit to do with magnets. So most of us have played with magnets, and you might know that a magnet has a positive end and a negative end. And when you have something that has a positive end, it's going to have a pole to it. We call that a pole. So where you would have a positive part, where you would have the positive pole of a magnet, and where you have the negative part, you would have the negative pole. The planet Earth has two poles. We don't call them positive or negative. We call them north and south. So where you have two distinct regions of something, you would call it a pole. In the case of a magnet, we call it positive and negative, and molecules are not too much different than this because of the presence of the electrons, and whether the electrons are being shared equally or not can create a positive pole or a negative pole on a molecule. So let's look at that. So let's bring back our water molecule. So what we know is that we have this oxygen sharing with a couple of hydrogens. And in this image, I've drawn something a little bit different. I've actually made my oxygen very big, and I've made the hydrogen really small, because that's actually very true of the size of these atoms. Oxygen is pretty large atom, and hydrogen is a pretty small atom. And as a result, oxygen has a very large electron attracting capacity. And even though it invites hydrogen into a sharing arrangement, what actually ends up happening is that once it gets a hold of that electron, it hogs it. So we don't see an equal sharing. So when oxygen has electrons, it's going to hold them really tight. It's going to keep those electrons tucked right in. And what we end up seeing then is that most of the time oxygen is going to have the electrons and hydrogen is only going to have them part of the time. Now, because electrons bear a negative charge, wherever they congregate, it's going to have a slight negative charge too. So in water, the oxygen is always going to have a slight negative charge to it because it's hanging on to those electrons with their negative charge most of the time. And it's going to leave each of the hydrogens with a slight positive charge because the only thing that has a charge in hydrogen when the electrons are not there is going to be that positively charged proton in the nucleus. This is what creates poles in a molecule. It is the fact that one atom is going to hog the electrons, thereby creating a negative region and maybe a couple of positive regions. This means that water has a polar bond. It means it has the unequal sharing of electrons. And because it does it with two hydrogens, it creates a pole here and it creates a pole there. We would say that water is a dipole molecule. Two poles, not just one, two, dipole. Now, what if we had two hydrogens sharing electrons? Well, the ability of this hydrogen to share the electron with this hydrogen over here is the same, which means that these two hydrogens are going to share their electrons equally. And it's not going to mean that one's going to have the electrons more than the other one. So there will be no polarity in this sort of a covalent bond. So this would be an example of a non-polar bond. Now you might be scratching your head going, well, how do I know who's polar and who's not? There are charts that you look at if you want to know. They're charts. There's no way to just kind of abstractly know this. You just go to the periodic table. Actually, you go to an electronegativity chart and you look there and look it up. And then you do a simple calculation to find this out. But that's not what this unit is about. This unit is understanding what is creating this sort of polarity, and it is the ability of one of these atoms to attract the electrons more strongly than it is the other one. Now, if you want to know how to do that, like I said, look up electronegativity chart and you can figure it out on your own. And then you'll see why this is true. It's because both of these hydrogens have the same sort of electronegativities. Oxygen and hydrogen have very different electronegativities. Oxygen is very strong, hydrogen is pretty weak. Hence, polarity. So as we just saw, nonpolar covalent bonds are going to be the equal sharing of electrons between atoms. It's going to be electrically balanced. There's not going to be any charge anywhere. An example of this is that hydrogen gas. Whereas polar covalent bonds are the unequal sharing of electrons between at least two atoms, and it's going to result in an electrically polar molecule, that is a molecule with a negative region and a positive region, at least one, and the result is going to, an example of that is going to be water. Water is the classic example of a polar molecule. So understanding all of this polar, nonpolar business may seem rather abstract, so let's bring it home to a real-life example. Let's look at water. Why are we so concerned with water? Well, mostly because we're mostly made of water. Our blood, mostly water. A lot of water in our tissues. We need water to survive. So we need to understand water. Now, the thing we know about water is that it is a polar molecule. And as a polar molecule, it's going to bring with it certain behaviors that we need to be able to understand in order to make determinations about nutritional needs and how drugs will behave in the body and you know, things like that. Chemistry things. All right. So the thing that we know about water is that it's going to have this negative region as well as a couple of positive regions. Now, what does that do? Well, remember, this molecule is not going to necessarily be living by itself. It might be living with other molecules, like other water molecules. So what's going to happen between these other water molecules? Nothing? Oh, no. We've got these very active reactive molecules with these positive and these negative regions. So what will happen is that this little hydrogen molecule that's operating in an electron deficit, because it has decided to share its electron with oxygen, which is an electron hog. Basically, all the electrons are right here. This little hydrogen with its electron deficit is going to look over here at this oxygen with its electron abundance and say, hey, do you mind if I kind of like, you know, share some of your negativity over here? And as a result, it's going to create this force in between the molecules, a very powerful, in fact, the most powerful intermolecular force, which is called a hydrogen bond. So important that we call it a bond. It's not truly a bond, but that's what we call it. So what's so special about hydrogen bonds? Well, it's this electric attraction between our electropositive hydrogen, or our hydrogen operating in an electron deficit, and it's being attractive to an electronegative atom, in this case another oxygen in a different water molecule. So that's what a hydrogen bond is. Not a true bond, like I said, more like a magnetic attraction. But we see this commonly with molecules that have a polar or a dipolar presence, such as water. And in fact, it is this quality of water that makes it liquid. So this little attraction between this electron-starved hydrogen and this electron-abundant oxygen is what allows water to be water at room temperature. That's very powerful. What other powerful things does this sort of hydrogen bond do? Well, right here, it holds the two strands of DNA together. That's how powerful hydrogen bonds are, is that there are molecules in our strands of DNA that have little electron-starved hydrogens that are looking to atoms on the opposite change and forming these bonds strong enough to hold our two strands of DNA together. In fact, I believe that typically shows up as a board question, so you might actually put a star by that in your notes. And I remember it was on my boards. I've taken two sets of boards, and the question was simply, what intermolecular force holds the two strands of DNA together? Hydrogen bonds. So there you go. So that's how powerful hydrogen bonds are. We wouldn't be able to have an understanding of hydrogen bonds if we didn't understand about the polar forces at work in water, which means that we needed to understand how the electrons behaved, which means that we need to be able to understand how atoms are put together, which is how we started this entire lecture. And this is the end of USLO 2.2. Thanks for watching.